Hello, in this video we will talk about concentration units, specifically molality and mole fraction, but we'll throw some other concentration units in there as well. Alright, but before we start, let's review the terminology on solutions. So a solution is a homogeneous mixture of two or more components, and by homogeneous we mean that on a very small scale it looks uniform throughout the solution. There's not obvious flecks or clumps or something like that. Now, in a solution, the solute is the substance that's present in smaller amounts, and the solvent is the one that's present in a larger amount. A little memory trick is that the word solvent has more letters in it, so it's the one that's bigger. You have more of it. Alright, some other terminology. Two liquids are miscible if they're completely soluble in all proportions. For example, you could mix water and ethanol in whatever proportions you like. 1% water, 99% ethanol, the other way around, no problem. On the other hand, you can have two liquids that are not miscible, and then it's almost like you have a solid going into a liquid, and then there's solubility concerns you have to worry about if they're not miscible. Alright, moving on. A saturated solution, it's our word for saying that a solution contains the maximum amount of solute. What that maximum amount is depends on the solute, the solvent, and the temperature that you're at. An unsaturated solution is less than that. And then it's possible to have a supersaturated solution where you have more than the maximum. And that's a little weird to think of, so let me talk about an example, which is sodium acetate. So these pictures below, on the left one you have a dish that inside you have a concentrated sodium acetate solution. And how you make a supersaturated solution is you heat it up and you dissolve as much sodium acetate as you possibly can at the high temperature, and then you cool it down. And now many solutes will crystallize or come out of the solution if you do this. However, sodium acetate will make a supersaturated solution. And the kind of simple way to think about this is, imagine when you make a supersaturated solution that the sodium acetate molecules just kind of forgot how to make a solid. And they're like, I kind of forget how to make a solid. Alright. But if you put in a little tiny bit of solid sodium acetate, so that's what's happening here. They're adding a little bit of solid sodium acetate. We call this a seed crystal. Then this will cause all of your dissolved sodium acetate molecules to, in effect, think, hey, that's how we make a solid. And then, zoop, it very quickly makes a solid, it crystallizes across the entire solution. Kind of crazy, but it actually does that. Alright, let's continue and talk about concentration units now. So previously we've talked about molarity a lot. It's the kind of default chemistry way to talk about a solution. This concentration unit is nice because it tells you how many moles are in some volume, and it's really easy in the lab to measure out volumes, and so that's kind of just easy to deal with. So I'll just throw an example here of how to make the concentration of something in molarity, or how to figure out the concentration in molarity. And I'm just going to kind of put the answer up because this is something you should already know how to do, but feel free for this and other examples to pause the video, work it out yourself, and then compare the answer. Okay, so in order to do molarity, which is capital M, you need moles of solute over the total volume of solution. So first, find the moles of solute. Here you go, convert grams to moles for sodium chloride. And then we'll use this 5 grams of sodium chloride throughout the rest of these examples, so it's at least consistent. Now we have the total volume. I converted milliliters to liters here, and you just do this division and you get the molarity. There you go, pretty straightforward. Do keep in mind that I will not give you the formula for how to determine molarity. That's something you need to know. Molarity, moles over liters. Molarity, moles, liters. Okay. Next up, mass percent. We use this sometimes in chemistry when we don't care too much about the precision of the number we're dealing with. And this is really commonly used in consumer products. They use this in biology a decent amount too. And it's a pretty straightforward thing. You're doing a percentage. You have the mass of what you care about, the solute, over the total mass, solute plus solvent. And so, for example, this little bag of IV fluids is labeled 0.9%. Granted, that's pretty ambiguous whether it's 0.9% mass over mass or We'll talk about volume percentages soon, and then that's volume over volume. Unfortunately, people often leave it ambiguous, which is one of my pet peeves. But sometimes you can usually figure it out too, just based on the kind of default characteristics of whatever it is you're mixing together. Alright, so an example here. And notice this is phrased differently. You have 5 grams of sodium chloride still, but then it's saying you add it to 98 milliliters of water. It doesn't talk about total volume anymore. It talks about how much water you add, which this is important because, alright, mass over mass, you have your sodium chloride divided by total mass, which is sodium chloride plus water. You need to know what the mass of water is because you need to add that to the mass of sodium chloride in the denominator here. So the questions have to be phrased a little differently. I did this little conversion from 98 milliliters of water to 98 grams per water, and I'm usually fairly explicit about that. If I want you to make that conversion, or I mean, maybe I don't want you to make it, but I might give you this information anyways, I'll tell you to assume that the density of water is 1 gram per milliliter, as opposed to making you just kind of go out on a limb and hope that that's right this time, because it's not always right. All right, do this math, you get 4.85%. Great. And I was just talking about this, subtle wording. Some problems you need the total solution volume, and other problems you need to know how much solvent you added. Depends on what you're trying to calculate. All right, I hinted at this before too, that you can have a volume percent, volume of a solute over total volume of solution. If your solute is a liquid, this is easy to deal with. You can also have a mass over volume percent. That way you don't have to figure out the density of your solution and just use the volume as is. And they're abbreviated in all these different ways. So say you're taking 5 milliliters of hydrogen peroxide and then filling it with water to make 100 milliliters solution concentration. This is pretty straightforward because we just did this. The answer is 5%. Do note that you can't take 5 milliliters of pure hydrogen peroxide. It explodes if you do that. So they usually make it, and the most concentrated solution you can buy is 37%. So you're never going to just pipette straight hydrogen peroxide. But when thinking about it in this problem, that's the way you had to think about it. All right, another one to talk about is mole fraction. And this is symbolized with an X, or sometimes it's the Greek letter chi, which we spell C-H-I in English if you're talking about the Greek letter. And so we use this in vapor pressures and phase diagrams of mixtures a lot. And this is effectively a percent of moles. So it's the moles of the solute you want divided by the sum of the moles of all the components, except it's not multiplied by 100. Just typically when you use the mole fraction, you wind up multiplying it by things, and it's much easier and you get much better math if it's not 100 or 50%, if it's 0.5 or 1 mole fraction. All right, here's our example for mole fraction. You have some mass of sodium chloride and some volume of water. Now, here's the moles of solute over the sum of moles of all. That's the formula, doi. And I won't give you this formula on a test either. It's something you should just know. It's pretty straightforward. It's like a percent, except you don't multiply by 100. Now, here's converting the volume of water into moles of water. And again, I tell you to assume the density of water is 1 gram per mil. And then now, we previously calculated moles of sodium chloride, so now we can figure out the mole fraction of sodium chloride is moles of sodium chloride divided by total number of moles, and it gives us this number. If you were to then turn it into a percent, it'd be 1.5%, but we don't do that with mole fraction. Now, you can also think about the mole fraction of water. You could redo this calculation and replace 0.08 with 5.55 in the numerator, or we can use the fact that the mole fractions of each of your components, of all your components, will add to 1. Just like percentages of all the components add to 100%, here they all add to 1. And so you could write mole fraction of sodium chloride plus mole fraction of water equals 1. You can then rearrange it this way and then solve for the mole fraction of water, and hey, it's 0.9848. Perfect. All right, now we're moving on with more concentration units. Here we have molality, and this is mainly used for colligative properties because when we talk about colligative properties, we're talking about things that change temperature over, I don't know, maybe kind of a wild temperature range, and you want a concentration unit that doesn't change with temperature. And so the molality doesn't change with temperature. It's moles of solute, just like molarity, divided by kilograms of solvent. So instead of total solution volume, it's mass of the solvent. And the volume of 1 liter of water is pretty much 1 kilogram, so molarity and molality come out to be pretty similar. We use this lowercase m for molality. Please don't confuse it with meters or mass or things like that. And then just like you can say a 2 molar solution, you can also say a 2 molal solution if you want to use the word that way. Alright, so now here's our example for molality. Same kind of setup as before. I'm not going to give you this formula on the test, you need to know it. So we've got to find the kilograms of solvent, which we can just take the milliliters and convert it to grams, assuming 1 gram per milliliter, and then go to solvent, like that, or go to kilograms of solvent, like that. Now do notice that I used just 1 gram per mil for the density. In the previous problems, I'd been good and I gave you 1.00 so that you know the amount of precision I'm having you assume. But that's not what we commonly do in practice. If you're going to make this kind of step in your calculation, you're going to introduce a little error into your calculation as opposed to using the correct density, but it's small, so it's not that big a deal often. But often we just say 1 gram per mil and we assume it's an exact number that doesn't limit our sig figs. So that's what we do here. We do it kind of the lazy way. Alright, now for molality, you need moles of solute. We'll divide by kilograms of solvent, just like that. And you get 0.873 molal. And now previously, when we did molarity on a pretty similar sample with a total volume of 100 milliliters, it was 0.856 molarity, or molar, I should say. And so these numbers are pretty close, 856 molar, 873 molal. They're usually pretty close. Alright, so a review. So molarity is the common chemistry way to go. Molality we use for colligative properties because it's independent of temperature. Percent by mass is also independent of temperature, and it's pretty easy to calculate and prepare solutions like this. You can also have percent by volume. And then a mole fraction gives you the exact molar ratios of something. It's effectively a percent in moles, except without the times 100. Alright, shifting gears. How do you convert between concentration units? This can actually be surprisingly difficult to do. So some hints. You can assume a convenient sample size to make your math easier. Concentration is a property that does not depend on how much of the sample you have, and so if you're going to convert between concentration units for the same given sample, if you assume some random sample size, it'll still work for all your mathematics, because the concentration doesn't change with whatever the sample size is. So often it's convenient to pick 100 grams, 1,000 grams, a liter, something like that, which you can then use mathematically to determine how your concentration exists in this other unit. Another thing we do a lot is use density to convert between mass and volume of the solution, or maybe the solvent or something. And there you go. Then you just have to kind of take these ideas and do some critical thinking and see what you can do. It just takes a while of playing with it to figure it out. So here's our example problem. We scoot it up to the top. The first thing we're going to do is figure out what we're going to do. So we have molarity, capital M. We want to go from moles over liters of total volume to molality, lowercase m, which is moles over kilogram of solvent. So we need to take the denominator, take it from total volume in liters to the mass of just the solvent in kilograms. And the moles on top is unchanged. So for this, we're going to wind up assuming a sample size. I'm going to assume 1 liter because it'll turn out to be handy later. If you assume a different sample size, that's okay. You'll still get the same answer. It just might be a little more work. Alright, so here's our 1 liter sample size. And this is sample size of the entire solution, ethanol and water. And we have the density of the entire solution, ethanol and water. So we can use that to find the mass of the whole thing. Great. We could convert this into kilograms and use it in molality if molality cared about total solution mass. It doesn't. It cares just about the solvent. So we need to figure that out. So 982 grams is the total solution. If we take the mass of the solute and subtract it from that, we'll then know the mass of the solvent. So first we have to find the mass of the solute. Well, we have the molarity of it. We have our sample size that we assumed. Right? This here is the sample size we assumed, 1 liter. And then you have the molar mass, the grams per mole. And then here you go. You have 60.8 grams of ethanol. Perfect. Now we do some subtraction. Mass of water, which is the solvent, is 982 grams minus the 60.8 grams. So the mass of the entire solution minus mass of the ethanol. And this gives us the mass of just the water. Now we're in the home stretch. We want molality, so we want moles over kilograms of solvent. So we have the moles of this 1 liter sample size. So 1.32 moles over liters times 1 liters gives you 1.32 mole. And I suppose I should write mole right here. And then you have the kilograms of solvent. I just converted from grams to kilograms here without showing it. And then you get 1.43 molal as your concentration. So it's kind of a lot, right? This is a lot of work and logic and kind of problem solving to figure this out. And so practice is key, and so we'll do a good amount of practice in class, and I encourage you to do more on your own. And when in doubt, assume a sample size and see where that takes you. And that's all we have for this video. Thanks for watching, and see you in class.